Differential equations govern the way that we perceive our natural environment. From population growth to chemical reaction rates to the launch of a rocket, we can describe nature as variables changing in patterns over time. In this manner, we conceive mathematics so powerful that they redefine our classical notions of matter. In order to gain a deeper understanding of differential equations, we need to go back in time to Europe in the 1700s, a crucial period in the development of differential equations. During this time, 3 men are credited to making diffie-Q what it is today. These are the 3 horsemen of space-time. We'll start off strong with the oldest horseman, the responsible older brother, if you will, a Swiss man loved by all his family and friends. This man was so prolific that to this day, his works haven't been fully translated. It's Leonhard Euler. Let's look at Euler's contributions to differential equations. He created the Euler method, a way to approximate solutions for ordinary differential equations. Let's break it down. The value that we want is y of n, which is the next value of dependent data. yn minus 1 is the previous value of dependent data. H represents the interval between steps. This is independent data and is usually a time step. Finally, we have the ODE part of the function. This is the derivative of the function at the previous value's interval or step. We'll look at a crude example in Euler's Swiss Alps. Here we have a paper boat floating down a river in a complicated XY path. We don't know exactly what the path is, but we can approximate it using Euler's method. We have equal time steps and velocities at those time steps. Using these velocities at t equals 1, 2, 3, and 4, we can get an approximation of the curve. This obviously works better with more time steps. But that's why this is just an approximation. The steeper the curve you have, or the less timestamps you have, the larger the error between the exact solution and the numerical solution becomes. So we either need a billion timestamps or have a super shallow slope. We're going to need another solution. Which brings us to the next horseman, the naughty middle child, born into an incredibly wealthy family from Normandy, France. He's conceited, competitive, and frustratingly smart. Pierre Laplace. Up until now, we've been working exclusively in the time domain with ordinary differential equations, or equations with just one dependent variable. Laplace's largest contribution to diffie-Q was the discovery and use of frequency domain to solve ordinary and partial differential equations. By transforming a signal into the frequency domain, you can see the motion of multivariable equations and get their real and complex parts. Then you can inversely transfer it back to the time domain and yield an exact solution. Let's go to Laplace's workplace. His colleagues, Fresnel and Biot, have just asked some serious questions about his particle theory. Instead of working it out, Laplace has decided to hit them on the head with some delicious, crispy French baguettes. So he gets some from the patisserie and decides to toast them up. He realizes, though, that there are too many variables for him to find the function of baguette crispiness with respect to the timer he set. He needs a toaster function, or really a transfer function, to connect these two and variables that they have in common. After finding this toaster function, he can put everything into the frequency domain by either using Laplace tables or this Laplace transform. Now, both potentially complex equations are in terms of S. They can be transferred back into the time domain to yield a real solution. Laplace transforms only work in the positive time domain, so we need a solution that works for the entire timeline. Our last horseman is considered the father of heat transfer. He was another Frenchman, but this time of much more humble beginnings. Eventually, though, he became so well renowned that Napoleon himself called on him to be the scientific advisor to the French army during the occupation of Egypt. It's Joseph Fourier. Much like Laplace, Fourier broke down complex signals into their basic component frequencies. Above is the Fourier transform and below is the inverse Fourier transform. We can see that we're now operating on the timeline of negative infinity to infinity. Let's say during Fourier's occupation of Egypt, Napoleon decides to climb to the top of a pyramid. After fooling around, he falls off. Boop. Fourier is going to see Napoleon's broken bones with an MRI. He gets a complicated signal from this MRI from the protons disaligning and realigning to a big magnet. This complicated signal can be broken down into its constituent, simpler tissue signals, which have a corresponding shade in the MRI picture. With a strong grasp on Fourier transforms, you can get an exact solution for nearly any differential equation. Thus concludes our journey with the three horsemen of space-time. I hope you learned something about your natural environment and are excited to go out and do some math.